So we are talking about confidence intervals now, which is a natural progression past sampling distributions. Basically, confidence interval gives us a reasonable range for where the parameter will be based on a statistic. This is an example that is in your notes, and we know that if the CLT conditions are met, then the sample statistic will be close to whatever our parameter should be. And our standard error formula is pt1 minus p over n, take the square root of that. Well, many times we don't know p, so we're going to have to use p hat in this formula. And because of the central limit theorem, we know that it's normal, and the normal rules apply, including the empirical rule. So when we move up or down 2 standard deviations or standard errors from the mean, then that tells us where about 95% of the data will fall. And when we take the mean and subtract and add the margin of error, which is that 2.5 percentage points, that gives us what we call a confidence interval. Basically, a confidence interval tells us how often our method of sampling will be successful. In this case, it will be about 95% of the time based on the work that we did. And there's an applet link that's in your PowerPoint, which I did a separate video for that one to let you see what we're talking about as far as what a confidence interval does. So confidence intervals tell us how confident we are that the parameter is between those two values that we come up with. This statement that is at the bottom is very important. This is one that we will use over and over and over again. We are whatever percent confident that the true proportion, whatever it is we're looking at, is between those two values. That is a confidence interval, and that is how you interpret every single one of them. All right, confidence intervals give us a range of values where a parameter might be. It tells us how confident we are that the parameter will be in that range that we came up with. It doesn't measure how one method or one sample works, but how the method that we're sampling works, as in the applet that's on the other video. There's this thing we come up with, which we will use a little bit, called alpha. Alpha is the level of significance. It's the portion of the normal distribution that is outside the confidence interval. So if we had not a good drawing, a 95% confidence interval here, then alpha would be this piece and this piece, which are both 0.025, 0.025. So in this case, alpha would equal 0.05. It is the portion of our interval, of our distribution, that is outside the interval. So for a 99% confidence interval, you'd have 1% alpha, 0.01. If for 90, you would have a 0.1, and so on. The point estimate proportions is the sample statistic p hat, and the margin of error is the calculation. And the z star, which is our multiplier, is determined by the confidence level. We have the standard error formula. So the form for any confidence interval that we come up with is always going to be this thing here. And I noticed I said point estimate because later on we'll use x bars instead of p hats. For proportions, this is our interval that we will use. If we do not know p, then again we use p hat in the formula. Steps to create a confidence interval, any confidence interval. Determine the confidence level, which would be 90%, 95%, and so on. We calculate the multiplier, which is our z star, and our margin of error, which is z star times standard error equals margin of error. We find the upper and lower bounds by doing the plus and minus. Then we write it as an interval in brackets, and we interpret it by saying that we are so much percent confident that the true proportion is in between those two values that we came up with. Here are some common values that we will use quite often. For a confidence level of 99%, we're going to use 2.58. For 95, we're going to use 1.96. And for 90, we're going to use 1.645. One note here, for the empirical rule, we said about 95% are within 2 standard deviations. The exact number that we're going to use now is 1.96. If you did it with your calculator, you would find it to be 1.96. 2 is just an approximation for that number. So how do we calculate this Z star if it is not the 90 or 95 or 99%? Well, let's go back to talking about what we had a minute ago. If we have this normal distribution and we want to find the multiplier to find a 98% confidence interval, that means that we're talking about an interval that contains 98% of data. Well, the alpha for this is 0.02, which means each end will have half of that because of the symmetry. And so I need to find the z-score that matches this information right here, where if I start here and go all the way to there, then I've covered the 1% and the 98%. So to find this one, it is inverse norm 0.99, which equals 2.33. The other one for 89, well, 1 minus 0.89, show you a different way to think about this, equals 0.11. Well, half of 0.11 is 0.055, and then I subtract that from my total distribution because there's going to be this much on each end. So for this one, it's going to be inverse norm 0.945, which equals 1.60.